So yeah, last week we didn't actually hold one because, you know, week 6, it's the crazy mid-sem assignment week, so yeah, I was busy.
It's called Quiet Week.
Okay, fine, quiet week or whatever. Yeah.
It's supposed to have assignments.
True. Anyways, last week I was actually supposed to talk to you about the projects that we were talking about. So they're still on. So I was going to discuss, okay, so the whole point of projects is that, so after you can finish the course, we want you to like develop some sort of real life application of whatever interest you like. So some topics could be like you know, in Sydney, the transport, this was Nikolai's suggestion. We have congestion and traffic and all of that crap. There's actually online data sets for free which show you the congestion on trains and bus congestion and all of that. So if you want to predict, for example, the congestion of like at 10 o'clock or something, and on Monday, you can do something like that. So that's just an example. You can use like a real life Sydney trains example. Predict. So yeah, all the methods we learn in class you can just apply directly. You don't need to know anything extra. Yeah.
If you're interested in the Transport for New South Wales dataset, I'm currently in the process of writing up an API guide for some basic projects to do with that.
Cool.
For the IoT course, so I can make that available more generally if you're interested.
Yeah, if anyone's just asked Nikolai. Yeah. Also, someone asked before something about questions, like actual questions for the course or something. That's actually, we do have questions now. So you can do that also if you don't have any idea, if you want to do the projects, you can just do the questions. There are solutions to the questions. However, the only issue is that the questions are in R. The solutions are in R. So if you want to do it in Python, that's the whole point. So you're not allowed to look at the R code. If you want to do it in Python, you have to do it by yourself. But we have like a specification. So other things that you can do with the course, for example, sentiment analysis. You want to classify, for example, if you have Donald Trump's tweets. Some of them are positive, some of them are negative. But which one's positive, which one's negative? You want to automatically classify them. So today we're going to learn about sentiment analysis and those systems. How we're actually going to classify text as positive tweets or negative tweets, or probably neutral, something like that. You can also do, so anyways, in data science, you can actually apply your skills anywhere, right? Whatever question you like, all you need is data, and then you can do whatever you like. So I was just giving you examples. Like if you're worried about sustainability, or you want to project, for example, you don't believe the global sea level rising data. You don't actually believe that, right? You don't believe the UN's projections. Well then, go and project it yourself and you will see that it's actually correct. Using any type of model, the projections show that global sea levels will keep rising. So you can actually do that yourself and verify that UN's data analysis is correct. So yeah, you can do lots of stuff. Anyways, the projects will be due, actually there's no really due date, it's just the end of this term, semester, so any single time. If you complete it successfully, you will get a certificate of completion. Yeah. In the advanced one and the introduction, I think I'll just use them for now. So no matter if you're part of the advanced one or the introduction one, if you just complete it and it looks like as if you did stuff without copying, like no plagiarism, then you will complete the course, that's all. Okay, anyways, I'll go into natural language processing. Okay, so there are 4 main, if you remember from the first few lectures, I told you that there were 4 main fields of AI, right? So you have your big AI, right, and there are 4 main fields. Well, in terms of algorithms. The first one is tabular algorithms. Right? These are just tables of data, and we want to do something with it. Right? That's the first one. So what are the other 3? The other one is natural language processing, computer vision, and reinforcement learning. Right? These are the 4 different subtypes. Well, there's actually more. However, these are the 4 main ones that are driving economic growth in the artificial intelligence field. Right, so we'll be mainly focusing on tabular algorithms at the beginning of the lessons. Right? So these ones are what we have been doing, like linear regression, decision trees, everything has to be in tables before you can do anything. If they're not in tables, you can't do anything. Right? So this is what we have been focusing on in the last 4 or 5 weeks. Right? So today I'm going to change to natural language processing. So in terms of tabular algorithms, if you're a data scientist, approximately, it should be 100% of all data scientists should know tabular algorithms. Right, I think the actual number is 97 something. I don't know why. Why is there a 3% discrepancy? But everyone should know tabular algorithms. Linear regression, logistic regression, easy, whatever. Everyone should know. Okay? Now, would someone like to guess how much percentage of data scientists understand natural language processing? What's the percentage?
20.
20, very good.
You
20?
today.
Oh, I wrote it. Oh, okay. 20% of people only understand natural language processing. How about computer vision?
No idea.
Also approximately 20. Right? But remember, this 20% is not additive. So it's not someone who understands natural language processing and computer vision is 40%. It's multiplicative, so 20 times 20%, which is very, very low for people who understand both at the same time. And reinforcement learning is, I think, like 1%.
No, there'd be overlap.
No.
Yeah, there is overlap, that's right.
Exactly. Yeah.
I forgot about that. Yeah, there are overlaps. But anyways, as you can see, everyone should know tabular algorithms. The issue is natural language processing and computer vision is very low. Right, and so I'm going to focus on natural language processing first, and then I'm going to go on computer vision. Reinforcement learning will probably be next semester, depends. So reinforcement learning is like self-driving cars, DeepMind and all of that. So that's reinforcement learning. Computer vision is your facial recognition software and stuff like that. Like Xbox Connect and blah. Natural language processing is Google Translate, Amazon's Alexa, Google Home, blah blah blah, all of that. The
Siri.
legal bots.
Siri.
Yeah, Siri, oh, forgot about that. Yeah, Siri and blah. But anyways, we'll be focusing on natural language processing today. Extremely important. Okay, so why is it called natural language processing? Why is there the word processing? Right? How come computer vision is not computer vision processing? Or why is there not reinforcement learning processing? Right? There's actually a reason why there's the word processing and natural language processing. So the biggest problem with machine learning algorithms is that we have to make everything in tables. Right? Everything has to be in columns. Right? Column 1 is age, weight, height, and the y variable is, let's say you want to predict income. Right? And using the age, the weight, and the height of the person, you want to predict income. Right? Everything has to be in tables. This is just you know, the whole premise of machine learning algorithms. Everything has to be in tables. Right? However, the issue is if you have text, for example, a tweet is I am happy, pretend. And the second tweet is like I am sad. And the third one is I am angry or something, right? How do we actually translate this into table format? Because that's our aim. We want to translate this text into table format. So how are we going to do this? Would someone like to give me a suggestion on how we can translate this into tables? What am I going to do?
Split the word, and if the word exists, you will get a 1 on the label.
Okay, cool. Okay, that's a good idea. So what are the columns then? The actual word.
Probably 0 and 1 a lot of.
0 and 1.
Yeah.
Okay, so for example, if I see the word I, what happens? Then it's a 1.
Yeah, I think.
So something like this, if I see an I in the first one, it's a 1. If I see an I in the second one, then it's a 1. If I see an I in the third one, then it's a 1. Right? Something like this. So how about happy? What happens if it's happy? The next word, the column. Then the first one is 1, the second one is 0, and the second one is 0. Yeah, is that what you were saying? Yeah? Okay, cool. So that's correct. This is called bag of words. So essentially what we're doing is we're counting the words, all the unique words. For example, sad will be in another column. It will be just 0, 1, 0. Right? And anger will be another column. 0, 0, 1. Right? This is called bag of words representation. We're just translating this text into columns and rows of numbers. Right? However, this is binary, so only 0 and 1. If you have another word, angry, like I am angry, angry, that doesn't really make sense, but just to say that exists, right? There are 2 words angry, so you just increment the count to 2. Right? So this is just counting the number of word existences. So if you see angry again, then you just put 3. Right? So that's called bag of words representation. The actual algorithm is, the actual algorithm is, I have some sort of dictionary, so some sort of hash table of words, right? Currently it's empty, but I firstly go to the first tweet, right? I go to the first one. I see the word I. Is I in the hash table? No. So I add it into the hash table. And then I increment the count by 1. And then I go to the next one. Is am in the hash table? No. So I put it into the hash table. And increment the count by 1. And so on, right? Happy is not in the hash table, I put happy in. And then increment the count by 1. And then I go to the next sentence. I. Is I in the hash table? Yes, it is. So I don't need to do anything, I just put that increment the count by 1. Am is also in the hash table. But sad is not, so I add sad. Right, and I put the 1 over there. But the issue is these are empty. Right, so I have to put zeros here. And so on, right? And this hash table is called the bag of words. It's actually a bag of words. And this method is called count vectorizing. So you're trying to find the vectors for each tweet or each sentence. So it's just 1, zeros, 1, 2, 3, 4, 5. Just count. You're just counting the numbers. Right? Does everyone get that? You're just counting the words in each tweet. And you're just trying to make it into, so each row is a tweet, right? But each column is just the word and the count. Yeah? Okay, would someone like to tell me what's the problem with that method? So let's say I have 10 billion tweets. Okay, 10 billion. All the way down. Right, and let's say that the vocabulary size, so the actual bag of words, the size of this is 100,000. What's the problem with this method? So I have 10 billion rows and I have 10,000 columns. There's lots of zeros everywhere. What is the memory usage for that? So 10 billion columns and 100,000 10 billion rows and 100,000 columns, right? And if you store this in your computer, right, it's horrifying, right? 10 billion times 100,000 is 10 billion plus, 5 zeros. Not very good, right? Your memory will explode. If you assume, so billion has 6 plus 9 zeros, 10, 11, 12, 13, 14, right? So your memory usage is approximately 10 to the power of 14 bytes, which is very, 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 very bad, right? So the issue is, so how do we actually reduce this problem, right? Because it's too much memory usage, we can't actually do any computation on it. So we introduced something called sparse matrices. Right, so pretend we have 100,000 columns, right, and one of the columns is the word, anti-disestablishmentarianism. You know that long word, anti-disestablishmentarianism, right? So how many tweets actually use this word? It will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then I'll see a 1. And then 0, 0, 0, 0, 0, everywhere is 0. I only see anti-disestablishmentarianism one time in the tweets. Right, this means that all these zeros are, what happens if we remove these zeros? Like, delete all these zeros. I don't care about these zeros. I just care about this 1. So that's sparse matrices. Sparse matrices deletes all these dumb zeros, because zeros don't mean anything, and I only keep this 1. Right? And this is just a mathematical format. It will reduce your memory usage by a lot. I'm assuming at least 80% loss. So you just, divide that, by 8, and then you'll get a very, very, you'll get a much more memory efficient method. So I think lots of people get confused. What is a sparse matrix? A sparse matrix is the normal method that we use is called it's column-wise representation, column-wise sparse representation. So what is that? So how do we actually translate this into like a computable format? Because in normal tables, there's zeros everywhere, right? So instead what we do is we go down the column. So I'll show you an example. You don't actually exactly need to know this, but this is just technical details, extremely important for memory problems. And we'll use these concepts later. So for example, if the first word A, word B, word C, word D, just say there are 4 columns. Every else is 0, 0, 0, 0, 0, 1. right? 1, 0, 0, 0, something. Your tweets will probably look like this. And our aim is to delete the zeros. We don't want the zeros. So in column sparse representation, you just look down the column, and you see a 1, you write the 1. Right? And then you go up like this. And then you see the 1, you write the 1, you go down. You see a 1 over here, you write the 1, and so on. Right? You do it like this, and then you count how many zeros you skipped. So 1, 2, 3, 4, 5, you skipped 5 zeros. You keep going, you skipped 1, 2, 3, 4, 5 zeros. You skipped 1 0, and then you skip 1, 2, 3, 4, 5, 6, 7 zeros. So you only keep this information. Right? This is only a few numbers compared to this entire table. So you just count how many zeros you skipped. And you only keep these numbers. A 1, a 2, a 3, and so on. So your memory usage has dramatically reduced. Okay, so this is called bag of words. Okay, so I showed you how you can use bag of words. However, I told you that there is a memory problem, so we solved the memory problem. What are the other issues of bag of words?
Those things like I and M, those frequent words probably meaningless in calculating the outcome.
Sorry, what do you mean?
Some word like I or the,
Yeah.
those most frequent words probably will be useless to calculate
Very good. Okay, that's a good point. So, for example, so you were saying the words the, I, a, you know, those common words.
yeah.
There will just be 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1. Everything will be 1. But that's not very useful. So we delete the whole row because there's no delete the whole column. There's no point, right? Is that what you were saying? Yeah, that's a good point. So what is that called though? What are those words called? The, a, we, I,
Stop
am.
words.
Yeah, stop words. Those are called stop words. Right, stop words are all the common English words we use that are not actually meaning anything, right? So if you write I am happy, right? We can actually delete I am because I don't really care about I am. I just do happy. Just leave the word happy. Because I and am, you can see that in every single sentence. I am sad. I am angry. I am going to do something. I don't know, something like that. So you can delete these. These don't mean anything. And so stop words is just a hash table or bag of words of these words. So this includes the, we, I, did, you know, am, yeah,
There are
something like that.
150 of them, right? There are 150 of them.
Sorry,
There are 150 stop words, I think. 150 stop words.
something like that, yeah, I think that's right. Yeah?
Well, I mean, I guess it would depend the purpose of what you're doing, because if you were analyzing tweets from a politician, for
Yeah.
example, those words could be important. If someone says we instead of you in an accusatory way, or if they say I a lot, to, you know.
Yeah, that's correct.
For rhetorical reasons.
No, you're right.
Those are important.
So I guess it's up to the data scientists to decide whether you're going to use the stop words or not. So you firstly have to understand the context of the question. So yeah, if it was Donald Trump's tweets, for example, politics, then yeah, this I, you, me, it actually does make sense because he's directing intent at someone. Or maybe he's just saying something. So we don't actually know. But yeah, you're right. We have to consider the context first. Okay, but that's, okay, so let's just say we fixed the stop words issue. Let's just say that. What's another problem with this approach? So the other problem is that we deleted all the meaning of the actual text. For example, okay, let's say that I write a sentence, I sat, I don't know, this doesn't actually make sense. I sat on a cat or something. I don't know. And then you write, no, actually that doesn't make sense. I was gonna think of a word, like you can reverse the words and it's still, like it's a different meaning. Oh no, wait, I'll just do this. I'll open a book, right? And the store is open, or something. Is open the same meaning in both sentences? Well, yeah, well, depends. That's actually not a good example. Okay, whatever, just pretend. So clearly open, right, doesn't it, oh no, you can just write, I'll book a flight and I'll read a book. Oh yeah, okay, that's better. I'll read a book I'll book a flight. Right? Clearly these books don't mean the same thing, right? I'll read a book. Reading a book does not mean you're booking a book, right? Kind of thing. Right? The meanings are different. So the question is, does count vectorizer or bag of words understand this meaning issue? What do you think? Yes or no? I mean, the answer might not be actually no. But what do you think? Does it actually understand this issue? Or is it a better way to say that the machine learning model understands this issue? I'll show. Okay, so obviously the bag of words approach deletes this meaning of book, right? Because book will just be one column, right, of just ones and zeros. It just means book. I just see the word book, and then, oh, it's a, book. I don't actually know if it's booking a flight, or is it I read a book. I don't actually know this. So the bag of words actually destroys the meaning. However, if you have a machine learning model, the machine learning model will actually learn the meaning of book, right? Because let's say that I said, there's another word, read, as another column, and I see the word flight. Obviously, if I see the word book and read, that means I'm reading a book. But if I see so there will be no flight in the read and book. But if I see a book and flight, then it means I'm booking a flight. So yes, the machine learning model will actually understand this meaning. Okay, so meaning, the bag of words representation, so the actual table of values that I converted the text into the values, they delete all meaning. But the machine learning model will learn the meaning. Okay, so that's just a catch. However, there is other problems. Okay, so meaning, let's just say we fix that. Okay, so the bag of words does consider some sort of meaning, but it doesn't actually, but you have to actually use the machine learning model first. Right, so that's the issue. The other problem of count vectorization is that the actual ordering of the words don't matter anymore. So if you write I am angry, and you write angry I am, and then you write am I angry? Do these all mean the same thing? Well, probably the first two mean the same thing. But the third one does not actually mean the first two. But the count vectorization is just 1, 1, 1, 1, 1, 1, 1, 1, 1. They're all the same. Right? I am angry. These are the words. Each of your one is 1, 1, 1, 1, 1, 1, 1, 1, 1. So there's the problem. You delete, so what the bag of words did is that you jumbled up all the numbers, like you jumbled up all these word meanings. Right? Because they're all 1, 1, 1, 1, 1, 1, 1, 1, 1. They're all the same. Even with the machine learning model, you can't do anything. Right? Because they're all ones. But the meaning of each sentence is different. So how do we fix that? So that's the question. How do we actually fix this jumbling of words problem? Because so bag of words literally just jumbles all the words up and then it's just numbers, right? So yeah, does everyone get that problem? The problem of context. The actual context. So like I am angry, and then you ask the question, am I angry? Right? They're totally different. But the bag of words representation is exactly the same. This is just, you just convert this into a vector, it's just 1, 1, 1, and this is also 1, 1, 1. Right? Clearly, they're not the same. Well, if you include the question mark into your analysis, then you will change stuff, right? If you put the question mark as a word, then it will be 1, 1, 1, 1 and 1, 1, 1, 0. So you kind of do sometimes fix this issue of these issues, right? And also, I forgot to tell you, yeah, we're gonna.
What if you had two sentences? One's I love Sydney and hate New York, and the other one's I hate Sydney and I love New York.
That's also correct. Then it will write the whole sentence.
Seen as the same thing.
Yeah, that won't be the same thing anymore. So yeah, bag of words does have problems. Even if you put like the question mark, there is no question mark in your example, so it will still fail.
Just the order is different.
Yes, that's right. So bag of words literally. So even if you swap the column or like columns, like it's angry, am I, and you just swap these columns, nothing will. So even if you swap the columns of the matrix, you're not going to change anything. So what it means is that bag of words destroys the actual ordering of the words. But we know in English, ordering is extremely important. Okay, so how are we going to fix this issue? The ordering problem. Oh, I actually, I should introduce one more thing before I go to, I was going to go into word embeddings. But anyways, one more thing. Let's say that I don't delete the words the, I, am, like those ones, right? The stop words. Let's say I don't delete. Right? I don't delete them. And also, let's just say the tweets, well, not really tweets. For example, let's say that I'm talking about fruit. Okay, this is not a very good example. Just say I'm talking about fruit. And I see every single, nearly 80% of all my tweets about fruit, I always say apple for some strange reason. I like apples. Apples are great. Apples are green. Apples can also be red, right? You see apple, 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 apple. But they're not actually, it's not actually a stop word, right? Is apple actually a stop word? It's not really. So we don't remove the word apple, but we still have this issue of 1, 1, 1, 1, 1, 0, 1, 1, 1. How do we solve this problem? What are we going to do? It's not actually a stop word, but it's not that useful. Then we introduce something called TF-IDF, or term frequency inverse document frequency. And what this method does is it penalizes words which I always see. For example, if I see the word apple, this is the apple column, 1, 1, 1, 1, 1, 0, 1, right? What am I going to do is I'm going to just penalize all the apples. So a very easy way to penalize apples is just sum all of this. So you do 1, 2, 3, 4, 5, 6, so sum is 6, and divide everything by 6. So the new weight will be 1/6. This is just a very simple way, just divide everything by the sum of the whole column. Right? And if I see the word angry, but I only see it once, right? I'm just going to divide by the sum of 1. So I only see 1, right? So it's still 1, which means angry is much more important than apple, because apple there's no point. Right? I always see the word apple, it's not really important. But I only see the word angry once, and so it should be more important than apple. So you just divide by the sum. Okay, that's not actually how you do it, but just an example. So yeah, I was just telling you different methods. Okay, so now I'm going to go into word vectors, the way to solve this issue of ordering, and also meaning. Okay, I'll first give you an example of what is a word vector. Okay, so let's say that I have some sort of space. Okay, I'm not exactly sure what I'm going to say about space. Let's just say I have this space. Okay, so this, just pretend some sort of space which has all the word vectors, and I'm going to draw the word vectors. Right, so remember a vector, you start from the origin, right, but it doesn't really matter, I'll just show, yeah, it doesn't. Okay, so the word vector for woman is there, okay, and the word vector for man is here. The word vector for daughter is here. The word vector for son is here, okay, and the word vector for queen is here, and the word vector for king is here. Would someone like to tell me a relationship between these words? So we have queen, king, man, woman, daughter, and son. So if you just look at this space, the structure of this word vectors, what's the relationship between all these words? Oh, isn't it black? Oh, whatever. So as you can see, the gender female is always on top. Right? It doesn't actually mean females are better than males, but this is just in the word representation space. Okay? Just pretend. So as you can see, always the female is always above. Right? Queen, woman, and daughter are always above somehow. But what else? Queen and king has some sort of elevated level, right? A queen and king has higher level than woman or man, right? And daughter and son. Probably daughter and son will probably be down a bit. But as you can see, this is an example. This is word embeddings, and this is what it does. it encodes meaning somehow into this space, right? So let's say that I have another word, right? So let's say that I have a new word, apple. Where am I going to put apple in this space? Well, obviously apple is not related dramatically to woman, man, daughter, son, queen, and king. So I'm going to put apple over here somewhere. Right? And that's the word vector, so it's elongated. Apple's over there somewhere. If I have a new word, person should exist somewhere here, right? It's close to man. Actually, it should be somewhere here. The word person should exist somewhere around man, woman, and person, daughter, son, right? Over here somewhere. If I see the word president, then it should be somewhere here, right? How about farming? Farming should exist over here. Right? So this is just encoding, so this is kind of like encoding the distance between words. Similar words and similar contexts will exist closer together. So what's the word that matches, what's the word in between president and farming? Probably economy and government. Right? Because the president manages the government, which manages the economy, and farming is related to the economy, and apple is related to farming. Right? So everything is like connected in this word dimensional space. And this is what word vectors do. They project words into some sort of n-dimensional space, and then it has this relationship. Okay, so I'm going to discuss word vectors now. Okay, so this is just a snapshot of what word vectors do. Okay, so what's the point first? Let's say that I have two words, happy and sad. Just two words. How many numbers do I need to encode happy and sad? Just the meaning. So the word happy and sad. How many numbers do I need to encode the meaning of happy and the meaning of sad? What do you think? Someone like to have a guess? Just how many numbers? So for example, happy, what number should I assign to happy? And what number should I assign to sad? And it considers meaning. For example, happy I'm going to put as 1, and sad I'm going to put as 0. So what does 1 and 0 mean? 1 literally means the happiness scale. So I made a scale, well, it just should be reversed. Actually, let's do the reverse scale. 0 and 1. Right, this is the sadness scale. Sad is a 1, and happy is a 0. Right, this makes sense, because on the sadness scale, happy is 0, right? It's not sad. But sad is sad. So let's say that I have a new word. I put a new word is super happy. Oh, it's not really a word. Or elated, for example. Right? Elated will exist somewhere here, right? So it will be negative numbers, negative 1. Depressed will be here. Right? Depressed. 2. Right? And so on. Right? Maybe you're going to be like super elated. It doesn't really make sense. But whatever. You get what I mean? This exists on some sort of like scale. Right there. Now my question is, let's say that I put the word angry. Where does angry exist on this scale? Is it over here? Is it here, here, here? Where am I going to put angry? Is it somewhere over here? What do you think? Where am I going to put angry? Or where do I actually like put angry on this scale, on this line? Does angry exist in the happy side, or does it exist in the sad side? Or could it exist in both? And so this is actually the problem. If you encode words with one number, you're not going to go anywhere. So let's traverse the dimensions and just put another scale. Why can't we do that? You add another scale called the angry scale, and there, you encoded the word angry somewhere on this new two-dimensional space, right? But what happens if I want the word president? Can I put president on the happy, sad scale? Can I put president on the angry scale? Obviously not, right? So I have to put a new scale. So a 3-dimensional scale called president, for example, and so on, right? So as you can see, you can embed words in some sort of n-dimensional space, right? Because each scale actually means something. So in word vectors, that's what word vectors do. Word vectors embed, so Word2Vector embeds words into some sort of like, currently the biggest one is 300 dimensional. You can download it from the internet. 300 dimensions. So there are 300, dimensions. I can't actually visualize 300 dimensions, but each dimension actually has some sort of scale factor. So remember the old example, the woman, male, female, whatever that one? Maybe a scale of up means gender. The higher you up on the scale, the more female you are. The lower down the scale, the more male you are, right? Because we saw that in the word embeddings. However, remember we also shown that there was also the king was on top, right? And the woman was on the bottom or something, and man was on the bottom, right? So some sort of status relationship. So this scale of up could also mean gender plus status. And so scales can mean a lot of things. These n dimensions can be a combination of different meanings. So that's essentially word embeddings. Yeah, does everyone get that? So what are word embeddings? We're just trying to encode words into some sort of space. Because the problem is we need machine learning algorithms to understand text. Right? And the way to make machine learning algorithms understand text is to translate text into numbers. Okay, so Word2Vector has 300 dimensions. Let's just say it has 300. It doesn't have to. It can have 50, 100, 200, whatever, arbitrary number. It can even have 10,000 dimensions. But anyways, let's just keep with 300. So for each word, let's say happy, I'm going to have a vector of 300 rows. So happy, -1, -2, 3, 4, 5, 7, 8, I don't know, 300 of these numbers. And so for each word, I generate word vectors for each word, right? So it's just a row of numbers of 300 dimensions. And that's what word vectors do, or word embeddings. Okay, so the actual, so now we have to talk about how do we actually encode meaning in 300 dimensions? Is the human actually gonna adjust the knobs? And okay, so happy should be here, I'll move it across here a bit, sad should be here and I'll move it across. Does the human do that? Or that's very silly, right? The human has to look at all 300 dimensions and move the words across. That's not gonna work. So then we introduce Word2Vec. And Word2Vec is an algorithm that does what I just explained to you in computers. So what does it do? So the sentence, I am happy. And let's say that after 400,000 words, pears are yummy, for example. I don't know. Let's just say that. Right? There are lots of words in between. And there are lots of words over here. Sad, for example. Okay? So let's just say this exists, some sort of text which has this, this example. So what Word2Vec does is given some sort of word, okay, let's say the I just choose a word, I, okay? I want to maximize the probability of, so I'm going to select the word I, okay? And in the cost function, the probability of am given I, right? The probability of am given that I see an I want this to increase, right? Because if I see an am and I see I, this probability should increase. But if I see an I, right, the probability of sad given I should be dramatically low because sad is all the way over here. Also, the probability of the probability of pears given I should be also extremely low, right? We want to keep pushing the probability down, right? So the probability of pears given I, this should be a very low number, right? Up to 0 here. this should be an extremely high number, up to 1. Right, so that's intuitively what happens in Word2Vec. So the word that I selected is called a context word, or the context vector. Right, so what essentially happens in Word2Vec is I select a context word I, right, and then I look at the words around it. Okay, so the word am is over here. So the probability of the word am, given I want to maximize. I want to increase this. And then I look at the next word, happy. The probability of the word happy, given I want to maximize as well. And then I see another word. I don't know, I am happy, full stop. The probability of the full stop, given the I want to maximize. Right, so this is essentially what it's doing. You have a context word, so I, you look across the words around it, and I want to maximize the probability of it occurring. But then if you keep going, and I see the word pairs, right, it's too far away. So the probability of pairs, given I want to reduce dramatically. And then all we do is we sum all the probabilities up, and that's your model. Right? So you just do the sum of all the probabilities, right, of the word you see, given the context word, you sum everything up, and I want to maximize. That's Word2Vec. I want to maximize the probability of all the words given your context words. And you have some sort of window. So, you know this context, like I want to maximize, I just stop, I don't know, here. I only want to see 2 words after and 2 words before. This context word will shift across, right, and the context window will change, and so on. So that's Word2Vec. The loss function is to maximize the sum of all the probabilities. Okay, so but then what does probability actually mean? Yeah, did you guys get that? Like, I'm trying to maximize the words that are next to each other, but if the words are super far away, I want to minimize that, right? I want to reduce those problems, the probability. Okay, so our cost function for Word2Vec is maximize. I want to maximize the sum of all the probabilities of the words given your context word. So the question is, what is actually this probability of the words given the context word? What is this? Right? So this is normally, I'm just going to say it's cosine similarity for now. Okay, so what is cosine similarity? Remember, each word is 300 dimensions, right? I have 300 numbers. Each context word is also 300 dimensions. Remember, that's because we chose the dimensions of 300. It could be 10 dimensions, it could be 30, it doesn't really matter. But let's just say there are 300 dimensions. Right, so each word and each context word is 300 dimensions. So, cosine similarity, what is that? If I have 2 words, okay, if I say that the word vector W, so the actual word is here, and the context word is here, the cosine similarity of word and context should be close to 1. Okay? I'll show you. But if I have another, so given the context vector is over here, and if I have another word here, right, it's not exactly the same, it's not pointing in the same direction in 300 dimensions as the word, right? So this is not going to be close to this. So this number will be probably 0, for example. But if the context word and the word vector is directly opposite each other, so let's say it exists here, the word is over here, then the cosine similarity of the word and the context word is -1. Because they're pointing in directly the different opposite ways. Right, so what I mean by pointing, remember the scale of the sadness scale? The word happy is pointing this way, right? The word happy is pointing left. But the word sad is pointing here. Clearly, the cosine similarity of happy and sad should be -1. However, if I have another word, depressed is pointing here. So sad and depressed are pointing exactly in the same direction. So the cosine similarity of sad and depressed should be close to 1. If, however, yeah, so this is cosine similarity. It tries to capture the direction and the actual magnitude of the pointing, where you're actually pointing in 300 dimensions, right? And that's the probability function. So how do we calculate cosine similarity? I'm just going to give it a very simple. I'm just going to use the dot product for now. But cosine similarity is actually quite a complicated formula. But for now, I'm just going to use dot product. So this, the cost function, we change to maximize the sum of all the word vectors dot product with the cosine similarity, the context vector. Right. So what does dot product mean? Remember, I have 300 dimensions. Right, there's 300 numbers over here for the word vector, and I have 300 dimensions for the context vector. All I do is I do pointwise multiplication and sum everything up. Right, so for example, I see 10, 20, 30. This is the word apple. Sad is -2, -3, -5. The cosine, the dot product is just 10 times -2, which is -20. 20 times -3, -60. 30 times -5, -150. And I just add all this up. Right, so -80, -230. So the dot product of apple and sad is -230. And I just put this into that's actually the probability function. Obviously this is not right because cosine similarity, I have to translate this from a number. Cosine similarity is a cosine similarity of two vectors is a number that exists in -1 to 1, right? -1 meaning that the two words are totally irrelevant from each other. 1 meaning that the vectors are extremely close. And this number can exist anywhere on the scale, -1 to 1. Somewhere, it can't be -2 because cosine similarity doesn't allow that, the formula. I won't actually show the formula, but that's the cosine similarity. So actually, the dot product, I just mentioned an easier method. Just pointwise multiply and sum up everything, and I want to maximize. But in actual life, they use cosine similarity. Okay. Anyways, okay, so we have this cost function, maximize the total probability. And wondrously, it just works. Word vectors, these words get automatically inscribed in 300 dimensions based on this formula, right? Maximize the sum of all the probability, no, not probabilities. The cosine similarity of the context vector and the word vector. I sum all of these up, and you will actually get a model. So this is just a Word2Vec model. Not really, but this is the simple one. You also have negative sampling, but anyways, don't worry about negative sampling for now. Word2Vector does that. Maximize the sum of all the cosine similarities of the context vector given your word vector. Okay, so anyway, what's the point? Like, okay, let's just say I have 300 dimensions. So I take the whole dictionary of English, right? And I put it into 300 dimensions. Or let's say that I take all of the Wikipedia articles and all of the whole Wikipedia, and I translate each word into context vectors and word vectors. And doing that, all these words get encoded in 300 dimensional space. Right? And if you visualize the 300 dimensions, so we have to reduce this down to 3 dimensions. Otherwise, we can't visualize. The reducing stage are algorithms like principal component analysis. We were talking about that in the first few lectures. PCA, principal component analysis. Reducing the number of dimensions of data from 300 to 3. Right? However, the more common methods we use is TSNE. But anyways, it has a similar understanding with PCA, however, it models much more complicated relationships. But after we do dimensionality reduction of these word vectors, we can visualize it into this space. So we have word vectors for every single word now. Okay, so that's the aim. The whole point is we have word vectors for every single word. So for example, so now what we can do is we can build machine learning models. So let's go back lastly to the Trump tweet example. The one with positive and negative. Actually, let's do another. Just do simple. I am happy. Right, these are your words I want to classify. I am sad. I am very happy. And my intention is to classify this text as happy. So the first one is happy. The second one is not happy. The third one is happy. Right? And that's my intention. So what do I do is I already have word vectors for every single word. Using Word2Vec, I have the word vector for I am happy, sad, very. I have word vectors for all of them. So then what we do is we can use neural networks, recurrent neural nets, we're going to learn that later. But in recurrent neural networks, what you can do, or convolutional neural nets, 1D convolutional neural networks. So what we can do is we translate this into word vectors. So the first sentence is I, some sort of 300 dimensions. And the second one is am, also 300 dimensions. And happy, also 300 dimensions. The next row is I, then am, and sad. So in this table, there's no columns anymore. Each column is just a word, right? But the columns are not related with the next columns, right? This column is not related, so this row column is not related with this row column. So what we essentially did is we translated these words, right, into word vector form. So each of these rows is actually 300 rows. One row is actually 300 rows. So it's a 3D matrix, if you want to call it. Right, just assume, so if you see, if I have a matrix, right, each row, I have rows, right? Each row specifies the tweet. But if you just assume this row can extend outwards, right? And this, when you extend it outwards, it's a 3D row. So what we have done is we created a 3D representation of your text. And this 3D, right, has 300 columns, right? 300 like 3D columns. And the whole point is because we have 300 dimensions. If we have 300 dimensions, then your 3D box will be 300 by how many words you want to choose in your context, right, and the number of rows, right? That's how it will look like. If you choose 20 dimensions, then it will just be 20. Yeah, I think. What's the time? Is that correct? Oh, okay. Yeah, but anyways, so with word vectors, we translated these words into actual meaning, right? So I and am actually mean something now in this 300-dimensional space. And then we can translate these words into some sort of representation like this, and then we can train a machine learning algorithm on this, and then classify as happy. The machine learning algorithms that we can use to train this include recurrent neural networks, right? Recurrent neural networks models time series data, right? Obviously, if I see the word am, it is very related to seeing the word I, right? So recurrent neural networks models recurrent behavior, right? It models time series behavior. We can also use, so a method in recurrent neural networks is called long short-term memory, also gated recurrent nets. And these are just variants of the recurrent neural network architecture that provide even better approaches. Right? Long short-term memory is the method that probably I think Google Translate uses and Facebook translation uses. Long short-term memory. However, many people actually don't know that you can actually use convolutional neural networks on these things. Convolutional neural nets are normally for pictures, but treat these as signals, right? Treat this as a picture, and you can apply convolutional neural nets to it. And the method that we apply is one-dimensional convolutional neural net. Because it's only one-dimensional, right? We're only going across the rows. A photo is two-dimensional convolutional neural net. But anyways, using these methods, we're going to talk about them later. Yeah, you can do everything with text. I think that's time.
It's time.
Okay, yeah. Okay, that's the end. So next week, I'm going to talk about recurrent neural networks, convolutional neural nets, and actually, how do we actually create our own model in Python using these concepts that we learned. Yeah, just don't forget about the projects. To submit the projects, you just need to email, or you can just ask. Yeah.